So thank you to everybody to be there. So there is many slides, many on PV fundamentals. So sometimes I will say if you are interested on this topic, you can read because it's more theoretical how it's operate and things like this, and focus on more important thing. Okay. And don't hesitate if you have questioning when I'm speaking, I can answer. So first, I will present where I am from. I am from here. So you have the map of France. Here it is the Alpine space, okay? There is Italy, there is Switzerland. So we are not far from Switzerland and very close from Italy. We are just to cross a tube to go into Reno, Italy. I am in the National Institute of Solar Energy, INES, and which is one of the 4-point spot in France where we are dealing with renewable energy. So in Paris, there is the Institut Photovoltaic Île-de-France where they are dealing with mainly on new PV cells. In Pau, they are dealing with all kind of renewable energy. So gas, because there was gas resource in the past, and now they are working on biogas and hydraulics and things like this. And Promise, I will speak tomorrow about Promise, where there is a very specialized on high concentration, high solar concentration. And whereas in my institute, we are more dealing with integration of solar energy everywhere. So integration in buildings, from building to cities. There is also some study to integration in vehicles, in balloon for atmosphere, for space, to be autonomous. In this area, there is one graduate school, so for training from master to doctoral study, and this one of Institute of Technology for Environment, which is led by the CEA. So at INES, we are sharing the space between the CEA, Commissariat Énergie Atomique, Université Savoie-Mont-Blanc, and CNRS. And so my lab is in this building, which is called Helios building. As you can see, it is in the Alpine space, so there is mountain everywhere in the surrounding. Here there is a lake in front of the campus. And all of these are testing facility of the National Institute of Solar Energy. So going from control condition to full scale, almost full scales and real condition. The graduate school is a part of, our university is a part of European Alliance of University. Europe decided to create some European university. We are implied in UNITA University that is with joint university with Italy, Spain, Portugal, Romania, speaking that Romanian language. And we have several agreement and MOU, and I would like to have a MOU with IIT Guwahati, with UNSW, with Singapore NTU, with of course close universities, Saragosse, Turino, Genève, Hong Kong CTU also, and we have international running project for PhD. We have at that time a co-fund with Australia, and also national French and Singaporean research project with NTU. So the graduate school is organized between one training path for master student. One is dedicated to solar energy in terms of engineering, so it's called energy for solar building and cities, and one is about economic and business and law, because there is a lot of barrier in terms of the development of solar energy, in terms of insurance, in terms of business, and in terms of law. Who has the right to sell electricity, how you can sell it, how you can buy it, and market. There's a lot of issue. And one scientific poll, which is organized in 3 main topics with joint laboratory, my lab, LOCI, and LEPME is for solar resource at multi-scale needs. So LEPME is working on solar cells, and we are working on the integration of solar components. There is one scientific topic about solar resource digitalization for better reliability. So it's about all detection of fault, prediction tools, as I mentioned this morning, with 2 labs. One in applied mathematics, one in informatics and data treatment. And the third topic is around how to diffuse, to help the diffusion of solar energy. Is mainly done by a lab on economics and business, and one on law and insurance. So I will start to deal with integration of PV in buildings. So first I start from the physical process of the photoconversion, and then how we characterize this performance, the performance of the module, what are the issues regarding the integration of these modules, and what is the main, what are the main components of a PV system. What do you need if you want to install a PV system connected to the grid or off-grid? So as it has been shown this morning by Professor Kalita, there is 2 ways to produce electricity. First is thermal. If you can reach higher level of temperature, you can produce some steam, and then from steam generate electricity. Second is direct photovoltaic effect, where you are using solar cells. We will see in the next day also the different type of components for solar thermal, low temperature, low and medium, that we could use also for cooling with solar thermal, or for electricity. So finally, with solar technology, we are able to try to answer to building needs. Which and we have to know that a building and a city are the biggest consumer in terms of energy. So it's interesting to see some combination. It has been presented this morning some data about solar thermal. Here I'm presenting about solar PV. So it is extracted from the International Energy Agency, that said that it will be the solar PV, the largest renewable energy resource in 2029. There is a big rush in terms of development of this technology. As you can see here, solar PV is now over the wind, is over the hydropower. Sorry. At that time, what is the market where there is a more big installation? Since a long time, until 2000, it was Japan the number 1 in terms of PV. Then it was Germany, and now it has completely changed. There is a big rush about China. At that time, 80% of the modules are built in China. There's a big industry to produce, and thanks to the COVID crisis, they develop a lot integration of PV in their own country, because they couldn't sell during a period, they couldn't sell abroad. So they decide to integrate massively PV. So at the time is at China, Europe, which is number 2. It's quite simple. Of course, Europe have a green policy, high level of interest for environment, but it has also to notice that in Europe there is no conventional resource. Okay, there is some coal, but not too much in Poland. But there is no petrol, no gas, except in maybe in the surrounding of Norway. So the conventional carbonate resources are almost inexistent, and since there is international instability, the price of this resource, conventional resource, can increase. Since the war between Russia and Ukraine, for example, there is no more gas coming from Russia. It was a big problem. So Europe is pushing a lot for energy sovereignty. So to be try to push a lot renewable energy to be as much as and possible independent from classical resource. And then you have US, as you can see. But you can see that India, India, no, it's not on this one, it's the next one, has a big push in terms of integration and development of PV, and there is a strong increase. At the time, this year, the more big implementation was Spain, Greece, Chile, Netherlands. So all countries that want to be independent of classical resources. And so, yes, it is here that we see that India has a strong increase in terms of implementation of PV. There is still China, which is pushing a lot for the development of big PV central, and then European Union, of course, a lot of money to put on the development in every country of PV. It's quite balanced between BIPV, so integration in buildings as a rooftop, even now in facade, and utilities, so it could be big PV central or other kind of application. But BIPV is so a very important market when we see this. So there are several applications of PV. The first was for space at the beginning. I will show you a short history. Autonomous apparatus like in the sea for security. We will see Friday, I think, solar PV pump and many different other. For BIPV, there's a lot of innovation of different shape, different color. We have work on printing also on PV to try to mimic some stone, some wood. So there is a aesthetical effort to integrate. So in terms of history, the photovoltaic effect has been highlighted in 1839 by Becquerel. Then there was the first solar cell with efficiency of 1%, very low. Albert Einstein then has a Nobel Prize about the photoelectric effect explanation. That what we call forbidden gap. It allows the electron to change and to move, to migrate in the conduction band and to be collected by a grid which is at the surface of the material, so by micro wire. Okay, so it's the main principle. The atoms are excited by photon. As the silicon is doped in one side positively, in other side negatively, thanks to bore and phosphor, it allows to favorize, to enhance this process of transfer of electron And the principle is to collect this electron to generate a current. Okay. So you can... In reality, with semiconductor, the energy which is useful is around wavelengths. Not all the spectrum, as this morning for the thermal, is useful. Only one part is useful. That means that regarding the spectral solar spectrum, there is a big waste in terms of collect, because one small part, around 20%, is collected and converted in electricity. The other part is heat, okay, which is not useful for PV conversion. It is not useful, but it could be a problem. If there is too much heat, the PV conversion is not good. That the efficiency will decrease. Okay, so 80% of the light is converted into heat, okay, and 10% could be reflected, and 10% converted, or it depends, less, more or less. Now we can expect to have 20% in the module in terms of efficiency. So different technology appear, so arsenic de gallium, GaAs, silicon, cadmium tellurium. Cadmium tellurium at that time is used for space application. It's very expensive, efficient also. Still the silicon, which is very well used, and because the principal resource is quite abundant on Earth. Amorphous silicon also is interesting, but so for silicon is around band gap is around 1.2 electronic voltage. So 1.2 EV is 10 power minus 19 joule. So it's very small amount of energy. Okay. So regarding the incident energy, some is lost because the energy provided by the photon is not enough for the electron to change, so it will generate internal heating. Okay, the electrons start to change and don't change, so come back, and there is photoconversion at the junction. There is also recombination between, so there are many physical phenomena inside the PV cells that more or less generate heat also. Okay, they are heat because the sun is heating the panels, but inside the PV cells there is also some phenomena that generate heat. So, and also there is a loss due to what we call parasite resistant. For example, if the surface is not perfect, if you have micro crack in the cells, or you can have a loss by Joule effect. Okay, all more or less is by heat, the loss. Okay, finally we model a PV cell like a diode. So it's going, the current is going just in one side, in one direction, from P to N. Okay, it's impossible to go in the reverse side. There is a resistance, parasite resistance that generate loss by Joule effect. And there is a shunt resistance which is linked to the normal resistance, electrical resistance of the PV module. Okay. For a cell, the voltage of the born of the cell is around 0.5 volts. The intensity that can circulate inside is around 20 milliampere per square centimeter. Very important data that are provided by us for a cell or for PV panels is This curve, we will see how we obtain that. Where you have, here you can see it is a maximum power, the product by intensity and the tension, the current and the tension is the power of the cell. It could be the same for modules. And so you see that there is a point which is a maximum power. The product of tension by intensity is maximum. So we call this peak power, okay, for a cell or for a module. This data is open circuit tension. So when your module is not connected, okay, and you measure the tension at the board of this module, you will measure open circuit, okay? When you have your module and you connect the two plus and negative, okay, it's a short circuit, and you will measure this intensity, short circuit intensity, okay? So all manufacturers should provide that, and it is provided at 1000 watt per square meter and at 25 degree, okay? And the efficiency is the maximum power by the product of short circuit intensity and VOC. Okay, the voltage is depending of the temperature, and it is this reason why I started to work on this field. Because originally I'm not from electrical engineering, I'm from thermal. But since the beginning of the 2000, I told you that it was the first massive integration in building. And people that were designing PV for building, after 1 or 2 years, say, I don't know, this PV central didn't produce what I was expecting. But I'm an expert on PV and I don't know. And the reason is that the temperature, okay? The temperature level when you are integrating in buildings is higher than when you are not integrating in buildings. And generate a lot of issue. Now we clearly identify that it generates also aging of PV panels and so on. So voltage is depending of temperature and intensity, of course, about radiation. Radiation is important also to generate electricity. So temperature in one side and electricity. So here you have some curve depending of different level of irradiation. Okay, you will see. For different level of irradiation, the intensity will change. Whereas for different level of temperature, the voltage will change. Okay, of course, the power will increase or decrease. Okay, so the power will decrease regarding the temperature. And it is the first attempt to find solution to decrease this temperature, to the idea of hybrid photovoltaic thermal, how to recover a part of thermal energy and to maintain the operating condition for PV panels. We will see that it's not so simple, because if you want to have heat, you want to have to increase the temperature, and sometimes it's not good for the PV function. So we have to find a compromise. Okay, it's clear for everybody. So an important thing that voltage is depending of temperature and intensity of radiation. Okay. So the method to test in normal operating condition. So normal operating condition is 1000 watt per square meter 25 degrees. Okay, so it's a flash generator. Here it's better to see. It's a big one. You see the flash test is at Ines here. You put the PV panels here, because now PV panels could be very big, part of big windows or facade, and here you have the flash test. So when you are flashing, the system will provide this. So the intensity V curve, okay, and the power, okay. So you can easily find with the power, which is tension at maximum, intensity at maximum, and the open circuit tension and the short circuit intensity. Okay, so it's easy now also to recognize a classical IV curve. You have 4 parameters: short circuit, open circuit, tension at maximum, intensity at maximum, and of course at the result. You can add some filter on such apparatus, because it's a flash, so you can add some filter that allow to displace the solar spectrum in one range of will filter such a range of wavelengths, decrease the global irradiation. Okay, you can play with that. I forgot we spoke this morning with atmosphere mass. So the standard for PV is to see that if the sun will cross the equivalent of 1.5 the width of the atmosphere. Okay. If the sun is perpendicular to the point, he is crossing 1 atmosphere. If he's not perpendicular, he's crossing, could reach 2 atmosphere, okay, on the pole, for example. So for PV, the standard of the solar spectrum is 1000 watt per square meter, as if the sun was crossing the equivalent of 1.5 the width of atmosphere, okay? So AM 1.5. So here is some documents if you want to go deeper on PV. So the classical technology are crystalline. So you can see here. Here we can see that it is polycrystalline. You can see different way to reflect the light. Okay. Here is monocrystalline. There is no different aspect, and I will explain you how it is manufactured. Typically, one module has 34, 36 cells that are in series, so all connected. Okay. But now you have a lot of different ways. You can have 2 parallel series of. It's like a fractal system, finally. What you find at the scale of a combination between cells, so parallel series, it's the same at the scale of a PV central. You can do the same, okay? So different technologies, the more common are monocrystalline, polycrystalline, and as I told you, there is now a lot of different technologies. The more studied at that time are perovskite, but perovskite are full of expectation. At that time, the lifetime of perovskite is very low. It whereas this technology are still operating after 30 years. 35 years. Operating is not a problem. It's the efficiency that they have, which could be a problem, okay? Usually, the manufacturer gives some warranty. And the usual warranty they provide is after 25 years, okay, of operating, your module will have 80% of the original efficiency. Okay, you start at T0. After 20 or 25 years, the manufacturer will say, guarantee that the efficiency will be 80% at the origin. So it's not so bad. Okay. So there is we are speaking about generation of PV cells, and so of course is to increase the efficiency and to reduce the cost. At that time, the cost is very low because there is a lot of resource, a lot of PV panels on the market. As I told you, Chinese manufacture a lot of PV panels, and they were stopped during COVID time. They couldn't export anymore, and they were keep on manufacturing PV. And so after, when the market opened again, the price decreased because you can find everywhere some PV panels at low cost, and and it is still the case. Okay. Okay, what's this? So, polycrystalline, monocrystalline. Now the efficiency are keep on increasing. For monocrystalline is more to around 23 to 24 of efficiency, and for multicrystalline is a bit less. So the difference between mono and multi is related to the manufacturing process of the PV cells. And I will explain you how it's manufactured. Amorphous silicon, you can maybe have seen that. It's a non-rigid substrate, so it's convenient. You could put on a tent or you could use for camping. But the efficiency is a bit lower. The advantage is that they are less dependent to the temperature than crystalline silicon. Okay, and the other technology, but we don't find too much. Thus, there was an attempt of using that, copper and indium. It has not been so developed. The advantage of this kind of technology, they accept more diffuse. The useful band of wavelengths is bigger. So it's not like solar thermal, but it's better than monocrystalline. They can use a larger band of wavelengths. So it was tested on Windows, for example, because on Windows there's a lot of diffuse radiation and different radiation. But finally it has not been so much developed for building application. You can find here some. Okay, you have some kind of ink or perovskite. It is like this. So it's a kind of ink that you put inside a polymer cover. And the main problem is that if this cover is aging, which is the case for a polymer, usually a polymer don't like too much UV. At one stage, if there is a failure, contact with humidity, or the cell is destroyed. Okay. So, but there's still big rush on perovskite cells, and the lifetime is still a problem for this. So you have many technology, many record, many ROS for the record, and you can see there are also some crystalline with multi-layers in order, we call that multi-junction, in order to use more wavelengths. So you can increase, now the best cells are more than 40% of conversion, but the price is of course expensive also because they are working how to trap the solar radiation at the surface. So there is nanostructuration of the cells in order to trap the maximum of sun, and then multi-layer treatment for multi-junction. But keep on, it's a big area. So how it's manufactured? So it is coming from sand, okay? And just to give you some idea, for electronics, the purity has to be 99.999% of purity for example, the processor of your computer. This quality is the same. It is a wafer, silicon wafer, but this is the purity. Whereas for PV, the purity has to be less, okay, less important. And the explanation, so you remember about the first manufacturer of PV cells. It was Total, Shell, BP Solar. The electronic industry at the beginning didn't care about PV. And all the waste coming from the industry of electronic was almost given to the industry of PV. Okay, it was waste, not useful anymore for semiconductor and electronics. So the company like BP Solar, Total were buying it for low cost and manufacture the PV cells. When there was an explosion of the PV development, the electronic company say, wow, why shouldn't use also our waste to produce PV? So they decide to keep on making electronic components and so on, but use the waste of their wafer to produce their own PV. That's why the original manufacturer disappeared, because they have no resource anymore. Okay, so that's why Sanyo, Sony, Sharp started to sell, and Total, BP Solar disappeared because they couldn't buy anymore. There was no specific silicon industry for PV. After 10 or 15 years, now there is specific production of silicon for PV. Not only for electronics and taking the waste to... There is specific production of silicon for PV industry. That is the reason why we have now new manufacturer, Q-Cell, Sun Power, and things like this. But it is funny to know the story of why it was BP and they disappeared, and because they disappeared because there was no more resource. So this is raw materials, silice, quartz. There is purification process. There is treatment. There is, I will show you, it is heating at a high temperature to melt, like the glass, okay? Then you have silicon block. You cut this silicon block in very small pieces with iron, with diamond, okay? The width of solar cell is around 150 micron, okay? So it's very thin. And then you treat, so you dope by bore and phosphor, and then you put some, it's usually some silver, okay, to collect the electrons and to bring it outside. It is a process. So it is the main reaction that are done, but the furnace are going at 2000 degrees. Okay, so it's quite high. So when at the end of this slide you have a life cycle analysis, at one stage there was criticism about PV. Say, wow, you have to oblige to reach 2000 degrees to manufacture the PV. You have a lot of process. Are you sure that your PV modules will produce as much as energy during his lifetime that the energy required for manufacture. And finally, yes. Oof. The answer was yes. But in facade, when you integrate in facade, which is not very optimized for the sun, it will be about 4 or 5 times. He will produce during his lifetime 4 or 5 times the energy that was used to manufacture it, whereas in roof it could be 10 times. Okay. So these are the main process. Okay, you are manufacture some block and you cut some slide of this block. Okay, treat, put the the connection and have the module. I will show you real image. So this is a big block, okay, of silicon. Then you cut this big block in lingo, in block, and then you cut all this in 150 micrometers. To treat, so this is treated and then to assembly. This is a real way to assemble because we work on colored PV, so we work with a company. So when all the cells are ready, you connect them in series. Then you put what you call the resin, EVA, and glass to protect the cells. And then you have again to heat. Okay, you have to heat, not at 2000 degree, but around 200, 150 degree to allow the EVA to melt. Okay. But what is very important is the temperature. So the manufacturer never gives the temperature. They heat the panels in order for the resin to melt. And the time, okay? Temperature and time is very two important parameters. They are important because they are conditioning the future evolution of the PV panels. You can have the same panels when they are manufactured. It looks like the same, but after in time, it will age differently if these parameters are not optimized. Time and temperature. You will see some bubbles that will appear after 2 years, for example. You can have delamination. I will show you some picture. The resin delaminate, whereas when they are just manufactured, you don't see nothing. Okay, so very important parameter. Here you can see some colored PV cells. It's the same PV cells that this one, but we have just changed the widthness of the anti-reflective coating. The blue color is a anti-reflection coating. Okay, like you have sometimes in your Google, you can see some blue. So it's anti-reflecting coating and optimized for the conversion wavelengths. Okay. If we just change this widthness, there is interference with wavelengths, which is difference, and we'll change the color. Only changing, it's like the butterfly wing. The butterfly wing are all made in the same way. It's some particles, but changing the widthness of this particle layer on the wings of it will change the color. It's the same principle. When you see different color, it's not being painted differently. It's just the anti-reflective coating width that has changed. Very interesting. Of course, you are losing a bit of efficiency because it's not exactly the anti-reflection coating for the wavelengths of conversion. Okay, but you can have the color you want. I will show you some pink color, we have played a lot with that. So you can change the color. Here the different way of that. Just why difference between crystalline and polycrystalline? The first process to melt the silicon is the same, but if you don't control the solidification, when this cool down, okay, you will have some solidification in the materials randomly, okay, and this random solidification will give you crystals, different direction of crystals. So that means that when you will cut that, you will see the footprint of these crystals, okay, and you will see that if it is not controlled. If you are controlling the cooling by magnetic field, you will impose to have a solidification in one direction. And so when you will cut, you will have one perfect surface without different footprint like this. So you will have monocrystalline silicon, except of having polycrystalline. That explains the fact that it is more expensive because there is more control during the manufacture. Okay. One other important thing is that during this process, the cut, the loss is very important. You can imagine it's very thin, and to cut 150 micrometers is very dangerous. So you have a loss at this stage around 50%. Okay, because if one of the cells is not perfect, there's a crack, there's a break. So then it returns at this stage. Okay, it can return till you have didn't put the PN treatment and the anti-reflective coating treatment. If you have already treated, you can't do nothing with this wafer. So it is also important thing that when you reach this stage and when you are dealing with life cycle analysis, it's difficult to do something with the cells after. You can recover silver, okay. You melt the silver and you can keep it, but the wafer which is doped, PN, plus with the anti-reflective coating, you can't do nothing with it. Okay. With that you can, but okay. So classical module characteristic. Usually the tension at the board of the PV is 24, 12 volt, okay? And you have to connect in series. So in series you had the voltage. In parallel you have the same voltage to build the PV central that you want, okay? You can reach 88 volts, more volts at the board of the PV central. They give you temperature coefficient, so for the intensity, for the tension, but what is very interesting, it is for the power loss. That means that you will lose 0.43% per degree compared to 25. Okay, I remind you that the tests are made at 25 degrees. So it never works at 25 degrees, especially if it's integrated in a building. And during summertime, on a rooftop, you can reach 60 degrees, for example. Okay, so you have a power loss, 60 minus 25 multiplied by 0.43. So in time, it could be important. That is the reason why there is focus on the operating condition of PV module. Now there is specific study on both sides of the PV module, because imagine you are in the city. In one side you have the building, So that means it is not naturally ventilated by wind or so the temperature is higher. And in the other side you have the urban climate, which is supposed to be higher also due to heat island effect. The temperature inside cities is usually higher than outside the city. So both sides of the PV module, you have extreme environment. So that's why there is also focus on the side of the urban climate. Okay, climate. Okay. Okay, so yes, the main point is that with increase of operating temperature, the efficiency is decreasing, but also the aging is increasing. We have noticed that the aging of these components they are aging faster. So the idea was to, okay, there is PV, there is thermal, we need both for buildings. PV don't like too high level of temperature, so there is a lot of research for integration and to try to cool down these PV modules. So typically, with vertical facade, we have worked a lot on natural ventilation, chimney effect. So when you have an air gap at the backside of the PV panels, try to enhance the natural ventilation inside by chimney effect, and to use this ventilation for engine of ventilation in the building, for example. You can put both, so you have juxtaposed system, PV and solar thermal, and there's a lot of study of PVT, so how to recover a part of heat. So as I told you, there is 80% of solar which is coming on the PV modules which is not used and it's lost in thermal. So you can play with that. The classical electrical characteristic I showed previously, already. It's the same at the scale of PV panels. So you can model the PV panels as you are modeling the PV cells. So you have a generation of intensity. You have a circulation of intensity due to the junction, Pn. You have the resistance of the PV panel, so the shunt resistance, and you have loss due to the bad manufacture of the PV panel. Every PV panels have a resistive loss due to the manufacturer. Okay, so the classical PV curve is very important. You have the fill factor. So the difference, the ratio between the maximum power and the open circuit and the short circuit intensity products will give you the fill factor. It's a very important factor which gives you an idea of the quality of the cell. Okay? Or the PV panels is the same. If the fill factor is important, that means that the PV panels or the PV cell are not in a good quality. Okay. If the fill factor is not so bad, it's not so far from 1, that means it is good. So it's a good idea also when you have PV panels to try to, because they don't give you that, for example. Or if you have also characteristic about the cells, it's interesting. So typically for monocrystalline silicon, the fill factor is around 0.83. Amorphous silicon is 0.7. Cadmium tellurium. So to give you an idea of the fill factor that you have to find for your module of your PV cells. Okay, so usually the PV modules has 12 volts, 24 volts, 48 volts. When you are in autonomous connection, you have also to have connection with battery, which has the same tension. Okay, it's very important when you have the PV central 88 volts to plug some battery in order to have also 88 volts facing this. So you are starting from the cells, the modules, and the PV array. As I told you, is quite fractal. It's the same behavior. Of course, between each you are introducing some loss. So here you have some loss due to the connection between the cells, also the glass, the resin, and here when you are introducing some loss due to the connection with cable, we will see that cable also generates some loss by Joule effect. Each time there is a loss by Joule effect. So, okay, so conventional important data are the power peak power at 25 degree, AM 1.5, open circuit voltage, short circuit intensity, and different characteristics. So usually you have this provided by the manufacturer. So the relationship between the power peak, the module surface, and the efficiency is quite simple. The power peak is equal to the surface multiplied by the efficiency multiplied by the standard radiation, so 1000 watt per square meter. Okay. So it is easy to problem. Okay. As I told you, intensity is depending of the radiation level. Voltage is depending of the temperature. The expected electrical power, okay, so is the power peak multiplied by the irradiance, okay, divided by 1000 watt per square meter. So you consider that at 25 degree, 1000 watt per square meter, the power is power peak, okay. When it is not 1000 but less than 1000, it is cross product. So it's power peak multiplied by the radiation divided by 1000. So it is what is expected from your panel at 25 degree without 1000 watts per square meter. Now, when it is not at 25 degree, you have to consider that. So it is very important that the tutorial that we will have Friday, I think, when I will speak about performance, we will see how from a real installation to identify the global efficiency. But it is a part of the demonstration. So I remind you, if you are in standard configuration, you should have this. If you are not at 1000 watts per square meter, which is very often the case, you have minoration by the real irradiation divided by 1000 at 25. And when you are not at 25 and not at 100 watt per square meter, you have to correct this electrical power. Okay, the electrical power that you have at 25 degree, you have to decrease it considering the temperature of the cell. Okay, we have seen that it was the temperature factor was minus 0.43% of loss per degree. Okay, so this is 0.43% per degree, multiplied by the difference between 25 degree and the real temperature. What we are use or manufacture or integrators are making some short cut, is that they consider this temperature as the ambient temperature, which is not the case. In this formula, Tc is the cell temperature, which obviously not easy to evaluate. But it's not for sure the ambient temperature. At least it could be the PV surface temperature, which is closer. But in reality, this formula is established by the cell temperature. So when you are modelizing your PV panels, you have to integrate a node of temperature at the level of the cell in order to have a better estimation of this power. Okay, it is cell temperature and not ambient temperature, which is for solar thermal efficiency, it is ambient temperature that we consider. Okay, so I told you the main advantage of silicon crystalline is that it is quite stable, quite mature. We have a lot of experience, of feedback on it, technology and so on and so on. The main inconvenience is that it is the most dependent of the temperature. Okay, it's around 0.5, 0.45 degree per degree. Whereas, as I told you, amorphous, for example, amorphous silicon is less dependent. It's 0.2, but the efficiency is less also. Okay, so you can have different evolution of different technology depending of temperature. Okay, there is some way to approximate the cell temperature. So the approximation is the ambient temperature plus the normal operating cell temperature. Okay, so it's 25 minus 20 is multiplied by the irradiation divided by 800 watt per square meter. So it's an approximation. There is more efficient model when you are modeling. This is more for practical evaluation. Now in some code, or you can find a lot of PV module models that provide you the cell temperature depending on the outdoor condition. Okay. Okay, the wind effect has also a lot of importance. You can see that on a real PV central where there is no wind, fully sun, and a kind of very short wind period, you can see that the temperature is changing and it will change performance quite a lot. So it is the reason why, as a BIPV, if they are not ventilated or not cool at the backside, you are inducing a decrease of the performance. So the wind effect has a big effect on the performance, but is not so well known at that stage. Okay, so small exercise now. I leave you some time to think about. So we have a photovoltaic modules of peak power of 250, well ventilated, with standard no temperature of 50 degrees. A temperature coefficient of minus 0.5, so it's quite high sensitivity. Submitted to a radiance of 600 watts per square meter, and an ambient temperature is 30 degrees. What is the electrical power delivered by this module? Okay, so we have seen that previously. Estimation of the module temperature or cell. We want to have the loss due to the temperature elevation and the electrical power delivered. This development, so we will see more deeply on a real installation to identify what we call the performance ratio. The performance ratio is a kind of efficiency, macroscopic efficiency of the PV central, trying to evaluate at each stage the loss. So the loss that could be to the temperature, could be related to the cable connection. In real life, could be related to soiling. Okay, I saw some PV panels on the roof. There is some soil, some dust on it. It could have an effect, and so on. So I give you the answer. So the module temperature. So we can go back to the formula. Okay, is TA, the ambient temperature, so it's 30 degrees, plus noct, so we said 50 degrees, minus 20, minus radiation is 600, divided by 800. Okay, so we have evaluation, thanks to this technique, of cell temperature of 52.5 degrees. You see, the ambient temperature is 30 degrees. So it's quite different. If you make the mistake to take, okay, the ambient temperature to evaluate the power generation, there is more than 20 degrees of discrepancy. Then the power loss is related to the dependency of temperature. So you have minus 13%. Okay, so compared to the power that you will read when you will buy the module, for sure you will have never this, and you will. Here it is not a very delicate operating condition. If you have 1000 here, it will be warmer, and so on and so on. Then the electrical power which is delivered is decreased with this, and so you have 129 watt. Sorry. Okay, so it's a way to evaluate, to simplify the evaluation regarding the characteristic of your modules, the evaluation of your electrical power that will be delivered. Okay. So, as I told you, more and more now we are looking also about the aging and the decrease of the performance. So these are classical decrease depending of the technology, okay, in time. So from the beginning you are losing quite strongly at the beginning, on the 25 years, for example, and then it's become more stable and more regular. But this is established in a controlled condition and in not a different operating condition. And we have identified that for specific integration condition in building, this could be huge. Okay, so as I told you, when it is not well ventilated or cooled, you have a loss of production, instantaneous loss, okay, but in time, the aging is faster. And so now it's also subject to study about that, depending of the operating temperature, mean operating temperature, are we able to evaluate the decrease of the performance in times. So this is also part of predictive model. I was speaking this morning, and also with a lot of data, these data were required in order to be more accurate, depending of the way they will operate, to evaluate the decrease of their performance in time. Okay. Now we will start. Do you have any question? Yes.
Let us say I have a situation that intensity is around 1000 watt per meter square, but my operating temperature is less than 25 degrees.
So it's better.
So then what will be the efficiency? It will produce more than the power it is producing in
Yes.
the standard display.
Yes. When it's cooler, it's a good question. For example, in our surrounding, in the mountainous area, during winter time, we have identified that the PV panels, PV central, were producing 25% more than what was expected. And there is two effects, and we want to identify which is responsible for another. There is first the albedo, because there is snow, and so there is reflection. Okay, but there is also for sure temperature effect, and so we will make some measurements to see which is responsible of on this global increase of efficiency. People that it was on a big parking for car park in the alpine ski station. They said, "Oh wow, we are producing more than expected, 25% every winter." So they were very happy. And so now we will try to identify which is the effect of temperature, which is part due to albedo. But yes, when it's cooler, it's better. So it is also explained why Canada, in the north of Canada, they are integrating PV central because there is temperature and albedo, which is interesting. Other question? Yes?
So we have seen that trend in architecture that most of the high-rise buildings in India are influenced by Western designs. That has glassy facades and windows. But India is much warmer compared to the European countries. With designs of big glasses and windows are now causing phenomena like artificial sun, which are causing the buildings much more warmer. So my question is that how can we integrate solar PV in buildings now, because they also have glassy covers, which can create similar problems.
I agree. It's a very good question and remark. Very good. At that time, we are investigating the fact that if we integrate massively PV panels in cities, what will be the effect on the urban climate? We have not yet the answer. There is a controversy about that. One is, okay, it is glass surface, it's dark surface also. But if we look at the global budget of the city, in principle, if all the surface are recovered of PV panels, in the global energy budget of the city, you have to extract 20% of radiation, which is converted in electricity and which go in the cable, in principle. That means that compared to the same kind of inactive facade, you will extract a part of energy through the conversion electricity and go in the cable. So some things that it will have no, it will not induce worst consequence. Some things that yes. So at that time we have a joint PhD co-tutel with UNSW on this topic, using meteorological tools in order to model quite accurately the local climate and to see the influence of such a surface on the heat island effect or not. It's a very good question where I have not the answer. And if the answer is yes, it's induce bad thing for urban climate. It is good for innovation. We have to find selective PV panels that collect what is required and reflect to what we call the atmospheric windows, the bad close infrared radiation. So it's a very good remark, but we have not the answer yet. Because if we consider that the main energy needs are in cities, we have to produce locally to use it locally. So we plan to develop a lot PV integration, but it is so a question, what will be the impact on the local climate, and the reverse, what is the impact of the local climate on the PV conversion? Because as I told you, it's very sensitive to temperature, but also radiation. Depending on the pollution, you have not the same as you shown this morning. And also the soiling, because in cities there's pollution, so soiling effect is important. Birds also, dust. So there's many issues that has to be investigated on this area, and very a big question that are interesting to answer. But we have not. If you look at the paper about that, you will find two different point of view. In my point of view, I think that it will allow to extract some heat in the energy budget of the city due to the PV conversion. Some don't agree. They said it's more dark, so they will have more convective heat exchange with urban air, so it will warm up the air and so on. So try. Yes, it's a very interesting study. Me, I for the side of PV, and the supervisor in Australia is from the side of urban climates, and we don't agree about the results. At that time, the PhD seems to find the results more in the sense of PV integration, that saying is not so bad, and the other supervisor don't agree with these results. Said that, no, it will warm, it will contribute too much to the temperature in cities. So, but we try to investigate that. Other question? So we can start on the. I don't know what time is it. I have 20 minutes to just start to try to cool down and to show you the different. So the simplest way to use solar PV is to use it when you are producing. Okay, so it is one of the lecture we will do. It is solar pumping. It was the first application developed by the petroleum company. There's a lot of book about that, solar pumping. So you connect your PV to a pump and then produce water, extract water when you need. There are also other application, but this is with battery, for example, whereas this is without battery. Okay, it's the most simplest way to use. So to use the sun, following the sun. Okay. Then you can complexify. You can add the battery because of course there is some energy need that you can't feel during the night. Okay, so you can have if you add a battery, it's better to add the components that is a regulator of charge and discharge. This regulator allows also to protect the battery for big peak of production. Okay. So if you add a battery, you can use it directly, but it's not really a good advice because yes, there is some fluctuation on the production. It will be not very good for the battery. So add a regulator. And with this kind of regulator, it's better to also add a MPP, so maximum power tracking. So it's electronic components that will determine, depending of the condition of radiation and the temperature, what is the maximum power. You see the curve, okay? And will identify this maximum power to fit with the PV production, okay? So this is good to win some energy efficiency of your global system. So with a battery, minimum regulator to protect the battery, okay? And if possible, as you are adding some electronics, to have both a regulator of discharge and charge and a MPP that will evaluate the maximum power of the PV central. Okay, and then, so for here you can, whatever the need, just charge the battery. And then when you need energy, you go on the battery. The second simplest way to use, okay? Then you can complexify. So you have the charge and discharge MPP, and you can choose to use when you need directly or to charge. Okay, to charge or to use. And also, if you use with continuous current, it's okay, but if it's alternative, you have to convert also. So to have an inverter that will each time you have a conversion, note that you are losing. Okay, you are losing when you are charging, you are losing when you are discharging, you are losing when you are converting a continuous current to an alternative. Okay, so each time you are losing part of energy. So you are complexify. So it could be good because you have flexibility of usage, but not that each time you are losing. You can have so MPP tracker and also that allow to convert continuous current in alternative current, okay, directly for the whole use. Typically, this could be applied for a grid connected. Okay. Now, more and more, we found hybrid system that when you are producing electricity, you can charge the battery if the price of electricity from the grid is is high. If the price of electricity is low, of the grid is low, you are using this electricity, okay, and you are charging your battery, okay. And if the price of the grid is increasing, you are using the current coming from your battery, okay. Now, especially in Europe, where the price of electricity can have big fluctuation, some are putting in their house some battery. You can have hybrid system with this is quite old also combination. There were combination of electro generator with petrol, okay, electrogen group and PV. So when there was no sun, this group, when we are not connected to the grid, produce some electricity. You can charge the battery and you can use it. So this kind of system is quite old also, but you can combine this with one turbine, for example, instead of that. So in terms of resource, there is a combination when you are disconnected. You can have only the PV that will charge the battery that will be used for the use, or direct use of this electrogen group. So you have many ways to connect finally. It depends of the way you will use your energy, okay? What are the needs? Are they constant? Are they during the day, during the night? So you can have many things. Now, as I told you, you can connect to the grid. And to use the grid also to charge your battery. If the price is very low, you have interest to charge your battery because you charge at a very low price. And when the grid price will increase, you stop and you use the charge that you have in your battery. I was speaking about sovereignty in Europe. This kind of principle is used at the bigger scale now. There is some attempt of storing some water in mountain, for example, for little village. So to create a kind of water loop, closed water loop, in order when the price of the grid is low, to pump the water at the higher tank, and when the price of the grid is becoming high, to use this dam to generate electricity for the village. It's a way to make money or to save money thanks to this capacity of storage. This could be used only like this, without sun, just playing with the price of the grid. When it's low, you charge. When it's high, you stop and you use it. Okay. But it is that it is this case. When the price is low, you charge, and when you are producing electricity, you use it as soon as you can for the day, for example. So you see, there are many. It's interesting to see all this configuration because it gives some idea of the flexibility. You have many ways. So there is not only one solution that I want to tell you. Even if you are connected to the grid, it's becoming interesting to add some storage, depending on the price. And there's many ways to connect and to use. You have to think about what is more efficient. Usually now the tools like Polyson, Archelios give you some advice about how to connect or what kind of components to add, depending on your needs. Okay. Whereas for grid connected, so it's quite simple. You have the photovoltaic. You have now obligation to be able to disconnect this from the grid, especially So this is compulsory in France for the fireman. If there is a fire in your house and you have a PV central, it's dangerous to put some water with electricity. So you have obligation to have a shutdown outdoor security. Then you usually have an inverter. We will see the way. You can have one inverter for the whole PV central. You can have one inverter for a string of PV in series, or you can have one inverter per module. Now there is micro inverter, so it's interesting. It's to have an inverter per PV module. Like this, you will not induce some problem in the whole PV central if one PV has a problem. So if the inverter is for each modules, it's avoid to have a mismatch effect and things like this. Okay, an inverter, monitoring usually to say what you are producing and then injecting on the grid and what you are using in your house, and electric meters until the electric grids. Okay, so it's more simple finally to be connected to the grid than to have autonomous installation where you have to think about the connection and the use. Here, it's not really a problem, you are injecting on the grid. Okay, except if you want to put a battery, so we are coming more in this configuration. Okay. Yes, the way to connect the modules. So it is in series, okay. You have to balance your installation, okay, and you have to connect the modules depending on the tension you want here, okay, especially for autonomous central, okay. Autonomous central, depending on the battery you want to put facing this central, you will have, for example, a 48 volt, okay. So you know that at each panel you have, for example, 12 volt, okay. When you are connected in series, you had the voltage. When you had in parallel, you had the intensity, okay. So you have to have a whole installation that will provide the voltage and intensity you want, and to be balanced. So the same module per string. You will not put 2 here, 3 here. It's not balanced and it's not good. The PV central will not work very well. You have the same inclination and orientation, and the same light condition. That means if this one at 3 o'clock in the afternoon is in the shadow of a tree, you will penalize the whole production. Okay, it's the same for PV modules. As all the PV cells are in series inside the PV modules, if there's a sheet of a bird on one cell, for example, it will create a big shadow on the cell, okay, and it will penalize the whole production of the panels. It looks like, oh, no, it's just a small dust, local small dust, but it will generate a decrease of the whole panel efficiency. And it's the same here. If there is one PV panel which is broken or on the shadow of a chimney or of the shadow of the surrounding buildings, it will penalize the whole production of the PV central. We call that mismatch effect. So they are not operating in the same condition. And if they are not operating in the same condition, they will be penalized. And of course, it is the panel which is operating at the lower level that will impose the lower level for everybody. Okay, It's not the higher best panels working in the best condition that will impose the best condition for the wool central. It is the reverse. It is the panels which is working the lowest that will generate a penalty for all the PV central. Very important. It's the same for soling. If there is a lot of dust, if for example you have just cleaning this and not this string will penalize the other. Okay, so that way for uniform soiling effect and so on, the way to clean the PV central is very important also. Not to start and stop here and start here. So yes, mismatch effect is very important to avoid. You can have on a same house, for example, east and west, 2 PV central, but they have to be connected independently. So that means that each central have to be its own inverter, its own thing, okay? So that means one will not penalize the other. So it's more expensive to double the materials, okay? I think for today we can stop. We have some question. So there is both track the maximum power production and then convert continuous current in alternative current to inject on the grid, okay? For the same PV central, you can find all the configuration to have one inverter for the whole PV central, to have one inverter per string, to have one inverter per PV modules. Of course, they are smaller, micro inverters. What could be the advantage and inconvenience of this solution? Why there is a choice? And we can finish on this. Compare the three. We consider the same power, the same number of PV modules. What could be the advantage on one solution compared to another? ID?
The last one,
This one? What for this last one?
because every panel is independent to each other, and damage in any one will be controlled there only, and it will not affect the others.
Yes, for this last one, each panel is managed by itself. So if, for example, this panel is not working very well, it will not penalize the other. Okay? The maximum power tracking is for him, the operating point is for him, and it will not create problem. Here, if there is a problem on one string, it will not induce problem for the other. Okay? But if this panel has a problem, it will induce a problem for the whole string. And this, if there is a problem anywhere on one panel, it will induce a decrease of efficiency for the whole installation. But there is, of course, advantage. The price. Okay? This is less expensive here than here, because there is less electronic components. Even if it is micro inverter, the wool will be more expensive than the centralized monitor management. Okay. But it's becoming very popular and very interesting for maximizing the performance of a PV central. Second is also if this is a breakdown, the whole central can't operate anymore. If there is a breakdown here, it will not affect the other. Okay? So efficiency and avoiding to stop the production. Here is the price because it's centralized, but it is less delicate to identify where there is a problem also, because you will see that globally on the PV central there is a problem because what is arriving here is not what is expecting, but you have to identify where is the problem. Here it's more easy also. If you see that at the end the production is not so high, it's very easy to identify which one has a problem, because usually they give some information also. Okay. Okay, so we can stop here for today. If you have any question, or don't hesitate. So tomorrow we make some examples on the sizing. Thank you. Oh, c'est bon.
Thank you very much. It's a very nice presentation. I think everyone got the idea of fundamentals of PV systems. Good. And same will continue to the next class.
Yes.
So, thank you for your patience. But I request you all, please be here by 9:30 tomorrow. And you can enjoy the campus. You can walk in the morning walk, evening walk. And then a lot of food stalls here. We will go around and you can taste food. Thank you very much.